Assalamu alaikum. Welcome to lecture 23 of data mining. So in the last lecture, we were discussing cluster validation. We were discussing essentially intrinsic techniques or unsupervised techniques for cluster validation. So we had discussed a number of techniques in that category. For example, we talked about the various intrinsic measures that are based on cohesion, separation, and hybrid measures. We also talked about evaluating through correlation or similarity of the clustering and the similarity matrix. And then we finally talked about the silhouette coefficient, which is a hybrid unsupervised technique for cluster validation. Silhouette coefficient, of course, is defined for every point, so you can evaluate the quality of the clustering of each point using silhouette coefficient as well. So today we will wrap up cluster validation with a discussion on supervised approaches for cluster validation. And then we'll start outlier analysis or outlier detection. So that's basically the agenda for today. Are there any questions? So we had already talked about unsupervised. So in unsupervised evaluation, we typically focus on intrinsic measures that are based only on the data set and some notion of similarity. And you can have intrinsic measures that are based on cohesion, separation, and both of those. And also we talked about cohesion, separation can be defined either through prototypes or through a notion of graph. And then we talked about comparing the similarity matrix with the clustering matrix. And the correlation between the two is also an intrinsic measure of cluster validation. We also talked about the silhouette coefficient. So today, let's talk about supervised evaluation. So in supervised evaluation, as the name suggests, we should have some data set that is labeled. So you should have labeled data set. So in other words, you have some data set D. D, of course, is your data set of X, I is equal to 1 to N. But in addition to the actual objects, you also know the grouping of the data. And of course, this would typically would not be available because if the grouping is available to you, then obviously you don't need to cluster the data. But this is part of the evaluation. We are assuming that we have some data which is labeled, and then we do clustering on the data, and then based on the cluster that are obtained, we compare those clusters to the labeled data. And as I said, this is only done for determining the quality of various clustering algorithms or comparing clustering algorithms. This is not the end game in the sense that clustering for labeled data is meaningless. We would like to do clustering on data that's unlabeled. This is only for evaluation purposes for comparing clustering algorithms. Okay. So grouping of data is available. Okay. And only meant for comparing. Okay. So once you have determined which algorithm is best, then you can go ahead and use that algorithm on new data set, which is of course unlabeled. Okay. So since we now have a labeled data set, the evaluation techniques in this category are very similar, or I would say even identical to those that are used for supervised learning approaches like classification. So we will have almost the same measures that are used there as well as for supervised clustering evaluation. So let's discuss all of these briefly because we have already studied some of these elsewhere as well. So the first approach is basically based on entropy. So just to, I will take some simple examples to illustrate some of these ideas. So let's say you have a cluster, and of course, this is after you have done the clustering. So let's say you have a cluster C, let's say C1, and this cluster C1 has, let's say, 4 objects. So 1, 1, 1, and 3. So this 1, 1, and 3 that I've written is the class label from the label data set of these objects that belong to this cluster. So in other words, we have found a cluster of 4 objects. Based on the labels that we have, we know that these 4 objects, 3 of these 4 objects belong to class 1, and 1 of them belong to class 3. So once you have these labels, you can always compute the entropy of this cluster. What is the entropy of this cluster using this standard entropy formula? So we have 3 objects that belong to one class. So 3 over 4, total number of objects is 4, of course, into log 3 over 4. So minus 1 over 4 into log 1 over 4. So you get a value which is 0.5, right? So this is the entropy of this cluster based on the labels that we have for this data set. So if all the objects in this cluster belong to the same class, let's say all of them were 1, then its entropy would be 0. So entropy 0 means that everything is homogeneous. And that is desired. That's the good end result, right? So in this way, you can compute the entropy of each cluster. And then, of course, you can find the entropy of the entire clustering as the weighted average. So let's say we have 2 clusters. The first had 4 objects, and let's say C2, let's say has 6 objects. Then E then would simply be 4 over 10 into E C1 weighted entropy, then 6 divided by 10 into E into C2. So this would be the entropy of the entire clustering. And since this is entropy, lower values are better. Higher values are not good, lower values are better. Okay. All right. So that is one way of quantifying the quality of the clustering by using entropy. So another approach that is used for evaluating clusterings is called purity. So purity is kind of related to entropy actually slightly different from entropy. So the purity of a cluster, let's say we have the same cluster C1. So we have one object belong class 1, class 1, class 1, and class 3. So the purity of this cluster C1 is basically the max of so let me write it in words. Max proportion of class in cluster. Okay. So in this case, so we have two classes. One is class 1, the other is class 3. So class 1 is proportion of class 1 is 3 over 4, and proportion of class 3 is 1 over 4. So basically, simply the fraction of the object belonging to class 3 over the total number of objects, which is 1 over 4. So in this case, so we have max of 3 over 4 and 1 over 4, which is basically 3 over 4. So the purity of this cluster is 3 over 4. So similarly, you can find the purity of other clusters as well. Okay. So if you have multiple clusters, you can find the purity of each cluster. And then the purity of the entire clustering is given in the same way, in the weighted fashion. Let's say we are taking the same example. So 4 over 10 into P into C1 plus 6 over 10 into P into C2. Okay? So this will give us the purity of the entire clustering. So purity, higher values are better. So entropy, lower values are better. Purity, higher values are better. So when a cluster is pure, its purity would be 1, meaning that all objects belong to one class. And of course, if equal number of objects belong to all the classes in a particular cluster, then of course it will be equal to 1 divided by the number of clusters, number of classes in that cluster. So if there were just 2 classes in a cluster and both of them were equal, then of course you'll get a purity of 0.5. Okay. So this is purity. So these are the two most common techniques that are used for evaluating clusters or clusterings in the supervised domain. Of course, you can always also use measures like precision, recall, and F measure or F1 measure. So these are also sometimes used, and they have the same definition as in classification. So for example, if we talk about precision, and again, let's say we talk about cluster 1. So 1, 1, 1, and 3. Okay. So the precision here would, so we'll have to find precision with respect to both a cluster and with respect to a class. So precision is not defined for a cluster and all classes, defined for a specific class. So for example, precision, in this case, cluster C1 and class 1. Okay. So what is precision? So precision is the fraction of objects that belong to a class that are retrieved divided by the total number of retrieved objects. Okay. So in this cluster, the precision of course for class 1 would be 3 over 4. So class 1 आपके पास 3 थे और total object इसमें 4 थे. Okay. Similarly, let's say आपने recall इसका निकालना था C1 और 1 का, तो ऊपर तो of course 3 ही है, but नीचे of course the total number of objects belonging to class 1 in the data set. So let's say data set में 10 objects थे class 1 के, तो ये 3/10 होगा. So ideally for a good clustering, if there were 10 objects belonging to class 1, all of them should be fall into one cluster. So if a cluster has retrieved only 3, then the recall is of course 3/10. Okay. So and of course F measure in दोनों का would be the harmonic mean C1 of 1. It's basically equal to 2 times precision into recall divided by precision plus recall. Okay, so this is the harmonic between those two values. And note that we are computing this for one class, not for all the classes. There might be multiple classes, and we are computing it for one cluster. So, and if you want to take the average of one cluster, average, you see, if you wanted to take find a value for a given class for all the cluster, then you have to do the weighted average as we did before. So for example, let's say मैंने पूरे clustering का recall निकालना है, तो then this would be, of course, recall for class 1. So class रहेगी हमारे पास. So 4 divided by 10 into recall of C1 and 1 plus 6 divided by 10 into recall of C2 and 1. So this now would be the recall for the entire clustering, but for class 1. So multiple classes को combine करना relatively मुश्किल. Of course, you can take the weighted average also, but usually separately ही हम दिखाते हैं उनको. So if there are, let's say, 3 classes, so recall of class 1 आप separately देंगे, recall of class 2 separately देंगे, recall of class 3 separately देंगे. So you don't have now just one major, but now you have 3 majors. So any questions? So these are the techniques that are used in the supervised domain. There is one other approach which is somewhat similar to the correlation-based approach that we saw under the unsupervised approaches. But now this would be supervised. So let's look at that as well. Similarity or correlation-based evaluation. Okay, so now we have, previously we had the similarity matrix and the clustering matrix. So now we have the clustering matrix and the class matrix, the true matrix. So the clustering matrix, let me say this is C. This of course is n by n matrix, and Cij is equal to 1 if xi and xj belong to the same cluster. Okay? To the same cluster. And of course, 0. I'm sorry. So in addition to that, we have the class matrix. So let me call this, I don't know, L. This is also an n by n matrix. Okay. So Lij is 1 if xi and xj belong to the same class in the labeled okay. So if they belong to the same class in the labeled data set, then this value would be 1, otherwise it would be 0. So now we have two matrices, C and L, of the same size, n by n. So again, now you can compute the similarity element-wise similarity between the two matrices, or you can maybe compute the correlation. By the way, both of these matrices now are binary matrices. So usually यहाँ similarity is more appropriate than, let's say, Pearson correlation coefficient. So both matrices are binary. So more appropriately, we will be using some similarity measures that is appropriate for binary data set, like, for example, the simple matching coefficient or the Jacob coefficient. Okay. So basically, element by element, you compare. If the first element of C is same as the second element, it's the same as the first element of L, then of course you count as a match. If the second element is the same, you count it as a match. If it is not the same, you do not count it as a match, and divide it by total number of elements in the two matrices, which is n squared. Okay. And of course, a higher value would mean that you have done a good job of clustering, and a lower value would mean that the clustering is not good. So again, this is supervised because L, the matrix L, comes from the labeled data set, while C, of course, is the output of the clustering algorithm. So any questions? Okay, I think that is the end of clustering validation or evaluation. And also, I think more or less the entire section of clustering. I think I will mention a couple of additional concepts in clustering, but we won't go into the detail. You need to know this concept so that you can always look up the specific techniques under these ideas later on if need is desired. So usually there is the issue of clustering high dimensional data set. High dimensional data clustering. So each object is represented by some feature set. And if the feature set is very large, in the tens of thousands, then we typically say that's a high dimensional data set. So high dimensional data set, for high dimensional data set, we typically fall into the problem of curse of dimensionality, meaning that most of the objects will appear to be equally far away from every other object. So all of them would look like an outlier, unless the data is massive. You have lots and lots of data. Otherwise, each object will look like an outlier, and you think of it as noise. Okay. So in such scenarios, if you really want to find clusters, there are two general ways of doing it. First, one way is two general ways. Okay. So one is basically apply a die reduction technique and then clustering. Technique and then do the clustering. Okay. So the dimensionality reduction technique could be anyone that we studied earlier on, let's say PCA or SVD or even autoencoder. So once you have reduced the dimension using such techniques, and such techniques would typically remove those dimensions that contain less information and project your data set to a space, into a subspace which is informative. And then you can do the clustering in that subspace. So that is one class of approach. Of course, this is a two-step process. First, you do the dimensionality reduction or feature reduction, and in the second step, you apply an appropriate clustering algorithm like the k-means. So the second approach is basically find clusters in subspaces directly. Okay, so this is not a two-step process. In other words, you can say that in this set of techniques, the reduction as well as clustering is done together. Okay, so these typically are called subspace clustering techniques. Okay, so in this category, we can have you can have both. So subspace clustering, you can have both approaches. You can go bottom up or you can go top down. Usually it's bottom up. बॉटम अप में मतलब ये होता है कि हर एक डायमेंशन आप इंडिपेंडेंटली लेते हैं and see whether there are dense regions in that dimension. So once you have found dense region in just one dimension, then you combine it with other dimensions and together you see whether they are dense regions, and then you increase the dimensions. Okay. So, and there are some techniques in this area. We won't go into detail. There are many techniques, but the idea is like that. So let's say आपके पास, just to give you an example, let's say 1,000 dimensions हैं आपके पास. ठीक है. So you consider each dimension independently at start. ठीक है. So let's say एक dimension age थी, for example. So now just looking at age and the data that you have. So maybe your age for your data is spread between, let's say 30 and 80. अब इस single dimension में just one line, single dimension में आप देखें किस region में वो dense है. Let's say between 30 and 40 you have 50 people, while between 40 and 50 you have just 10 people. So 30 and 40 आप select कर लेंगे as a dense region in 1D. अब since this is age, then you now add another dimension. Let's say एक dimension height है. Height आपकी range let's say करती है, let's say 4 feet to 7 feet. इसमें आपने देखा कि dense region आ रहा है आपके पास 5 और 6 के दरमियान. So now you combine this age between 30 and 40 with height between 5 and 6, and this would, if this is also dense, then we have now found a dense region in 2D. इसी तरह आप increase करते जाते हैं. ठीक है. Of course, specific algorithms would have some additional tweaks, but this is the general idea. So this is subspace clustering. ठीक है. Examples of high dimensional data would arise in bioinformatics, for example. They would also arise in, let's say, document clustering. So if you represent a document with a feature set that consists of words, then that feature set would be very large. Usually words can easily go into tens of thousands. So unique words that represent or that are discussed in a set of documents can easily go into tens of thousands. So each document would be represented by a vector of size, let's say 10,000. So that's high dimensional. So this is one idea that I wanted to communicate. The other idea I wanted to mention was what is known as bi-clustering or co-clustering. So Bi-clustering or co-clustering, this is essentially somewhat similar to, you can say, what we have talked about in subspace clustering, but usually it is studied as a separate subheading under clustering. So the idea here is that, again, as I said, you had objects that are represented by features or dimensions. So in bi-clustering, you cluster simultaneously both the objects and the features. Okay? So you would be finding groups of features that would contain dense amount of objects, and you also find groups of objects that are also dense with respect to some features. So both together. So again, we have applications of this in bioinformatics and document clustering. So another application could be, for example, let's say you have movie recommendation or some recommendation data set. So let's say you have movies as objects, and for each movie you have, let's say 10,000 people giving ratings to them. So those 10,000 people are the features, but their values would be ratings. Okay. So now you can do co-clustering or bi-clustering, and maybe you will find groups of movies that are similar based on their ratings, as well as also you will find groups of people that give similar ratings. So remember, ratings are provided by people, so we are also grouping people. So applications do arise in recommendation system as well as in other areas like bioinformatics and word document clustering and so on. So document clustering में क्या होगा, आप documents के groups ढूंढ रहे हैं और word के groups भी ढूंढ रहे हैं. कौन से words हैं that occur similarly in documents. Okay, so these two additional concepts I wanted to highlight. They have applications in practice. All right, so any questions? Okay, so now let's move on to outlier detection. Okay. So outlier detection, I think, is chapter 12 in your book by hand. And you also have a separate chapter for outlier detection in the other book, Introduction to Data Mining. So let's let me start with maybe the slides, then we'll come back. So what are outliers? So an outlier is a data object that deviates significantly from the rest of the objects, or deviates significantly from the normal behavior that is observed from normal behavior that is present in the data generating process that is generating the data. So of course, this is a subjective definition, and by this definition also you can see why outlier detection can be difficult, because we have quite difficult task to quantify, for example, what is considered to be normal and what is considered to be significantly different. So both of these concepts, if we are able to quantify them precisely, then of course outlier detection becomes easy, but usually in practice it is not very easy to quantify these concepts easily. So ideally, so one other concept is outlier is part of the data. It's not noise. So noise is generally not considered part of the data. Noise is considered as extraneous information. Maybe it's caused by maybe communication error, maybe it's caused by human entry error, maybe it's caused by something else, some abnormal phenomenon that is not captured in the data generating process. So that's another difficulty of outlier detection. How do you distinguish it from noise? So, but conceptually, noise is different from outlier. Noise is not from the data generating process, while outlier is from the data generating process, but it is an object that is significantly different from the normal behavior of that data generating process. So the applications could be numerous. So you can have application in the financial sector trying to find fraudulent transactions. And there's also an example given here regarding sports. So Michael Jordan, for those who follow basketball, was a great basketball player. So his stats were significantly better than any other person. So that would be an outlier as well. But again, this is from the same data generating process. It's not an error in the data, it's actual data. Similarly, for the financial transaction, maybe it's an actual data. Of course, maybe your card has been stolen and you are getting those fraudulent transactions, but still it's from the data generating process. So if possible, we should remove noise before doing outlier detection. But as I said, sometimes it's not possible to distinguish between noise and outlier. If you have a model of noise, then you should remove noise before performing outlier detection. Okay, so let's move forward. Types of outliers are there are about 2-3 outlier types mentioned in these slides. Just give you a quick idea, although these are not very universally recognized, but of course they are defined in the textbook. So we have global, we have local, and we have contextual. So global, local, it's also sometimes called contextual, and then collective. So global outlier is generally a single point, a single object. Similarly, a contextual object outlier or local object is also a single object, while a collective outlier is multiple objects. So multiple objects together exhibit a behavior that is significantly different from the normal. You cannot identify or detect collective outliers by looking at just one point. We have to look at multiple points. So global outliers, of course, as the name suggests, is an outlier that's defined by some global criterion, while contextual outliers are defined by criterion that are context dependent. So that context could be local context. So if you're talking about GIS information, so local context would be some region defined by some latitude and longitude. So between this latitude and between this longitude, some space on Earth. So the context is defined. It's not over the entire globe. So again, contextual, of course, is usually also a single point. Global is also a single point. But as I said, collective would usually mean multiple points. So the usual example for collective is given is that regarding DOS attacks. So denial of service attacks in computer networks. So you cannot detect a denial of service attack by looking at just one, you can say one, what do you call it in networks? One transmission. You will have to, or one, you can say, okay, just one transmission, that should be fine. You have to look at multiple transmissions. Okay. So, and once you have looked at those multiple transmissions, then you will know that this is a behavior that is not normal in the normal transmissions on the network. So these are called collective outliers. Collective outliers. So then let's look at the techniques for outlier detection. Let's just quickly go over this slide as well. Challenges. So we have already discussed this before. So how do you model normal data, and then how do you quantify significant deviation? And then, of course, the challenges for outlier detection are all oftentimes very specific to the application. So the outlier detection that you typically would do in, let's say, bioinformatics would be different from those that you typically do in financial sector or in the telecom sector. So oftentimes domain knowledge is very relevant. For example, if you talk about outliers in computer networks, you need to know quite a bit about computer networking. And why is that? Because you need to know the normal behavior and the abnormal behavior. And then, of course, the issue of noise. As we mentioned earlier, noise is often very hard to distinguish from normal outliers because they look like noise. And unless you have a model of noise, then, and if you have a model of noise, then you can remove it before doing outlier analysis. And also a challenge is understandability. Maybe you run an algorithm for outlier detection, it would produce some outliers. But before that outlier is actually used by the end user or being deemed important by the end user, you should be able to, or the algorithm should be able to interpret or kind of explain why what this object was considered to be an outlier to the end user. So explanatory information is very important while finding outliers. Otherwise, they will be considered to be just random points and not be found useful by the end user. All right, so let's go back. So the techniques for outlier detection typically are either supervised from the machine learning context or unsupervised in nature. Okay. And they are also in the middle as well, semi-supervised, but I don't think so we should go into that. So supervised detection techniques would be something like classification that we studied earlier. So you have some labeled data set. So supervised, so labeled data set is available. Okay. So you have a data set, let's say D, X of course is the object which is represented with some features. And then you also have the label, the class label for each object. And the class label, of course, would be either 1, which means that it's an outlier, or it's 0, which means that it's not an outlier. So you have this label for some data set of your data generating process. Okay? So once you have that, then of course you can train a classifier to learn this model, learn this behavior. And once that model has been trained, then you can use it to detect outliers in the future. So this is the supervised way of doing it. So maybe you train a random forest for outlier detection. Okay, so we studied random forest earlier on as well as a classification technique. Given some label data set, you build a random forest. Once that random forest has been built or trained, you can use it to predict whether a new object xi is an outlier or not. Xi is either 1 or 0 using this random forest. So these techniques are generally called supervised. Of course, if you go into the detailed literature, there are some other techniques which are more tailored towards outlier detection. And one of them, those set of techniques, which we'll of course not discuss in detail, is called one class classification. So remember, classification is always classification between two classes or more classes. But in one class classification, it's also multiple class, two class classification, but we are tailoring it to one dominant class, and that dominant class is a normal behavior. Okay, so there are some techniques that are tailored in this way, and they are very appropriate for outlier detection, one class classification techniques. Okay, so these are quite appropriate for outlier detection as well, in addition to standard classification techniques like random forest or SVM or neural network. So now let's focus on unsupervised. So in unsupervised techniques, no label data set is available. Okay. So we don't have any label data set, and from this data set, we would like to find objects that are outliers. So in this framework, we have several categories of techniques. So let me mention those categories first, and then we will discuss them briefly. The first category, of course, statistics. So techniques. And then we have proximity based. And then we have clustering. And then finally, we have what is known as reconstruction. So in the unsupervised category, we have this further subcategorization. You can have statistical based techniques, we can have proximity based, and we can have the clustering based, and then of course reconstruction based. So let's briefly discuss these. So the statistical techniques basically involves statistical model fitting and then statistical testing for deviation. So you have model fitting, and then of course testing. So Model fitting, of course, would mean that, let's say you have some data set and model fitting can be parametric and non-parametric. Again, this is all from statistics. Parametric would mean that, let's say you assume that this model follows a Gaussian model or a bell-shaped type of distribution. And that bell shape has some parameters. You fit that parameters on the data, you get the model. And then given any new point in the data, you find out how different it is from that model. And again, you can do a hypothesis testing type of thing to find out the difference to some significance level. So this is the general idea in statistical techniques. But the challenge here and the difficulty, especially in real world applications, is that these techniques do not scale up for real world data sets. So they are good for hundreds and maybe even a few thousands of examples, but they are not good for tens of thousands of examples or objects. So these are more of, they are not used in practice in the data science field. So we're just not going to discuss this in more detail. Of course, you got the idea. You fit a model, either parametric or non-parametric, and then you consider each point and see how different it is from that model. And of course, you can apply some testing, hypothesis testing approach to quantify that difference in a robust way. Okay, so that is statistical. And then let's move on to the proximity. So proximity based, as the name suggests, is based on the notion of proximity or similarity. Proximity is the general name for similarity or dissimilarity. Okay. So this is the technique that is reliant upon a notion of similarity or dissimilarity. So within this, of course, there are two techniques here, and we will discuss them quickly. One is distance-based outlier or outliers, and the other is basically density-based outliers. So you can think of distance-based as prototype-based, and density-based as, of course, density-based, meaning that it considers multiple objects and the space in which those objects lie. And so let's discuss one technique in each of these. So distance-based outlier, it's a very simple idea. And this is, of course, a global notion of outliers. Remember, we mentioned global and contextual. So this is global outlier detection. So the idea is that we have a parameter, let's say two parameters actually. So we have a parameter, let's say R. We can call this parameter R as radius. And the other parameter is, let's say, pi, which is the percentage of objects that lie beyond this radius. Okay, so you need to specify two parameters. And then given these two parameters, so dB of an object O, some object O, and given these parameters R, and the other parameter is pi, the algorithm will tell you whether O is an outlier or not. So given an object O and the parameters, of course, which is R and pi, the algorithm will tell you whether O is an outlier or not. So how does it do that? It's very simple. So it basically constructs a neighborhood around O. So neighborhood O defined by R. Okay. So some points may fall within this neighborhood R, and the rest would be outside this neighborhood defined around O. So if so let's say n is the total number of objects in data set. ठीक है? ठीक है? And then let's say NO is the number of objects in neighbor of O. Okay. So which means that n minus n underscore objects lie outside the neighborhood. So if this number is greater than so percentage of objects, okay, ठीक है. So NNO is the number of objects that lie outside this region. Divided by n into 100, so that I convert it into percentage. If this is greater than pi, then O is a dB outlier. Okay? So this is the idea behind this. So again, you can flip the parameters. Maybe pi as defined in the algorithm is the percentage of objects that lie outside this neighborhood. You can complement it with another parameter, which is the percentage of objects lie within this neighborhood. Yeah. Of course, you will get the same result if you use the same complement parameter. Okay. So neighborhood में NO objects हैं, total objects n थे, neighborhood के बाहर कितने हुए n minus NO, इसकी percentage निकाल लें. If this percentage is greater than the percentage that you specify as a parameter, then this is an outlier. So for example, you might have R as a radius. Of course, this radius would be defined in terms of similarity if your data set is not Euclidean. If it is Euclidean, then this is, of course, the radius in Euclidean space. So let's say I just give some value 1 here, and then let's say pi, let's say आप कहता हूँ 75%. So if 75% of the data sets lie beyond the neighborhood that's defined by 1 around an object, then that object is an outlier. So this is distance-based outlier. उसने पाई की वैल्यू लिख दी उधर. ठीक है. All right. So this is, of course, what is the complexity for this algorithm? Of course, you have to visit each object in the data set, which is n. And then for each object, you will need to find its neighboring points. And if you have distance-based indexing, then maybe you should be able to find it in log n operations. But if not, then you will have to visit every other point also, which is n squared. So in the worst case, of course, this is n squared complexity. So most of the clustering algorithms are also n squared complexity. So this is similar to the complexity of algorithms, clustering algorithms. Okay. So the next technique that we are going to study is density-based outlier, and this specific technique is called local outlier factor, or LOF. So this would give you a notion of contextual or local outlier. So the first one was a global outlier. This would give you a local outlier. So what time do we have? 1:31. Sure. So we have two techniques to discuss, this one, and then we have the autoencoder. I'm just thinking maybe I can do this next time. I think I will discuss both of these techniques next time, so we can stop earlier today, what 5-10 minutes earlier. So any questions? By the way, this LOF that we are going to discuss is going to be very similar to the density-based clustering techniques that we talked about earlier, the DB scan, for example. And of course, as I said, this is density-based, so it is very similar to the DB scan technique that we studied earlier for clustering. So any questions? So we had 8 quizzes so far. So we are going to have 9 quizzes in all in this course. So the last quiz would then be next week, right? Tuesday, is that fine? And then the last 10 days, you won't have any quiz before the final exam, before the end of the semester. So if we take 9 quizzes, we'll be dropping 2 low scores from those 9 quizzes will be dropped. Okay. Any comment or question?